So any missing data is dropped. Thank you.
Should be working now.
Awesome. Welcome back, people. So we are discussing some details about the project. As a summary, I want to say that ranking scores can be the same, but they don't have the same meaning across students just because the relative position can be different. Other thing is here we are working with one record per student, so we selected the first the first uh, uh, the first application, because as I told you, students can have up to 10 applications. We selected the first one, so we had one record per student in terms of multivariate things, and the system stops once you were selected in one of your admissions. So I was showing you this. So this was our data set. Now, importantly, this was our dependent variable. As you can see, zeros and ones. Okay? The admission results. Those are zeros and ones. Admission results. 0, you were not admitted in your first application. 1, you were admitted in your first application. And I was mentioning this. You can see that approximately 276 students.
I don't think I've shared yet. Hang on. Sorry about that, Zoomers.
Oh, that was.
I got to reshare. There we go.
Thank
We're
you.
back. Okay.
Thank you. So approximately 276,000 students registered to take the admission test. This year, 2024, we had almost 300,000 students. So we have a large data set. However, we were interested just in those students who were exposed to the regular education curriculum, because the admission tests use that curriculum as baseline for the test construction. We have a special curriculum, but that's not considered. It's like a shorter version. So we considered that wasn't fair to expect a similar performance between students based on the curriculum they were exposed to. Then we had this reduction because not all the students who registered took the test, and then we realized that not all of these students with valid scores applied to selective programs. So you can see that this is almost 50% of the sample. Within this sample, we had those not admitted, 15,000, those admitted, 55,000. So that's better than considering within this N the amount of people admitted. Within this sample size, we had like a 50% of the students who were not applied, but they were not applied because they didn't even apply. Okay? So things that we do most of the time, a sample description, you can see how to do this, and here I'm using dplyr, I think. You can see that we must, sorry? R package? Mm-hmm. Yes, this dplyr is here. Yes. Yes, here is dplyr. So YR, yes. Inside dplyr, we have functions that works as verbs. We have select, mutate, filter. Those functions within this package help you to perform some data manipulation, and that's pretty cool. So you have the details in the code here. So for example, that helps us to create some specific statistics. So you define your variables and you say, these variables have these levels. So then show me things like the percentage using those levels as a reference for the factors, okay? Then we had a bivariate analysis. So here you can see the means across different characteristics. Importantly here, for example, in terms of language and math performance, you can see that people who graduated from humanist schools outperform students who graduated from technical schools. Now, that's something that researchers link to the orientation of the schools. Because in Chile, the humanist schools are dedicated to higher education. So you have, for example, biology, chemistry, physics. In technical schools, you don't have those subjects. You have some courses that prepare you to enter the labor market. Something like accountability, you have management, client service, or customer service. A fun fact about me is that I graduated from a technical school. So my performance in test scores was horrible.
You beat the odds.
But I did it. So then, for example, in terms of family income quantile, you can see that in terms of means, this type of differences in test scores, this is language, this is math, you can see that the differences are huge. So now this is a plot that summarizes some of these differences, and you can see that as the profile, as the characteristics of the profile improve, the scores improve too. So that's interesting. However, this is just description. We cannot analyze this in terms of causation or any of those things. This is just correlation. Well, not correlation, this is description. Yes, because these are not correlations yet. Okay, let's go. So, first model to fit is the empty model, as you saw here, because we need to have an estimation of what we are estimating, or an idea. So here you can see that we were using the GLM model. So the things that we learned here were applied in this research. And you can see here that when we took the logic of the intercept in our model, the proportion of ones was the same as the proportion of ones in the data. So what we were predicting was the probability of being admitted, the probability of 1. Okay? Then you will see here, if you are interested, some of the different models that we tried, because we saw in our first model, in the full model, some of the predictors were not significant. A school sector wasn't significant. Parents' education wasn't significant. That was interesting, because one of the things that researchers relate to performance, especially in math, is mother's education. Here wasn't statistically significant. So we had like a discussion about what to do with this, because the statistical significant is not always like the thing that you should follow. However, we had a lot of power, so we decided to remove that for this specific study. Likelihood ratio test to assess the relative model fit, and this is our final model. So we had the 4 academic predictors, and then we had a student sex, income levels, and school administration. So you can see that, for example, this means, this slope means that the logic of admission increases among students who graduated from private schools compared to students who graduated from public schools. Then we computed some R-squares, specifically the surrogate R-square, which substitutes your binary variable by a normally distributed thing. And then see the function looks for the changes in R-square. That's described in the paper that I cited somewhere here, if you are interested. But based on that, the academic predictors were able to explain approximately 10% of the variance, and the non-academic factors almost 4% of the variance. Then, for completeness, you have the other pseudo R-square measures. Finally, yes, 2 minutes. Finally, we plotted the odds ratios because they work as effect sizes. So here we can see that the school private was the predictor with the largest effect size. However, as Lisa mentioned, the meaning of 1 unit difference here is not the same for the case of a school than for the case of the test. So that makes these odds ratios hard to interpret sometimes. We know that this is the largest odds ratio, but one unit difference here means you are going from a public school to a private school. And we plotted the predicted probabilities.
I do have a question. So would that mean that if you're looking at odds ratios for like binary
Yeah.
features, it's going to look like it matters more because I see the thing on the left-hand side is also binary.
Yes.
Logical effects. But the things in the middle, which are continuous, appear to have less effect, but that's because of one unit increase.
Exactly.
It's so small.
Yes,
For 10 points on an 800-point scale.
exactly.
Yeah, it's not a fair comparison.
Yes. So in my experience, or what we did in this paper, we focus on the predicted probabilities among students. That's what we did. And here you have the function. We were using the prediction package, and then we got this plot. So you can see that, for example, when we compare males and females, males tend to got higher predicted probabilities than females for or across income quantile levels. Similar when we use the school sector as a control variable. Well, this is not control, but like a grid. And this similar when we consider mother education. Now, this wasn't in the model, but given that we had the probabilities, we could use it as a grid too. So that's the project. I hope that you enjoyed this time. Thank you.
Logistic regression, useful in life.
Yes.
Thank you for the example.
Unfortunately, the paper was rejected.
Tell them why. Tell them why.
Yeah, well, were two main reasons. First of all, was because I think that the reviewer was a Chilean one. Because in Chile, for some reason, at the end of the papers, in the conclusion section, we give guidelines about what to do with the results for policymakers.
Oh, that was bad.
And I know I don't do that now, but the reviewer wanted more implications about the results for the policies in the admission system, something that I think that we cannot do. The other thing was,
You can.
what do you see here?
Well, I noticed one very
Here.
interesting- yeah.
Sorry. Here, that's the school ID.
Yeah, is that in your model?
No.
So kids are clustered in schools and they didn't account for the clustering and that got it bounced.
Yes.
You can resubmit it.
Reason two was, if you have students in classrooms, why are you using single-level models instead of multi-level models? So, back in 2021, we didn't know how to fit a multi-level model.
Yeah, that's
I
why.
noticed that there was like a 0.7 something on the fifth
We're
level.
wrapping up, Zoomers.
Like it was like sort of the p-value. It's like, wow! It had basically nothing to do whether, if you're the higher income. It was like, you're going to that school.
So
That
he's
was it.
pretending students are independent, but they're clustered in schools, which means there's commonality that's being ignored. And I wanted him to say that because I'm teaching a class on clustered data next fall. So if you want to avoid having your paper rejected, then come back. All right, so we're wrapping things up. Thank you,
Very
Zoomers.
nice.
Thank you, Roomers. Thank you, Vladimir. Have good weekends. Work on your homework. Let us know if you need anything.
With the clustering,